Hello, everybody. Thank you for being here today. My name is Chaima. I'm a third-year PhD candidate at the University of Michigan, and I'm happy to have this chance to present my recent work entitled How Does Refactoring Impact Security When Improving Quality? A Security-Aware Refactoring Approach. Let me start with a brief overview of the context of my work. So software projects evolve and change continuously with the changing requirements of customers. And as the software changes, its structure becomes more and more complex. That's why understanding code is by far the activity at which developers spend most of their time. This reduces productivity and efficiency of developers as well as their motivation to work. Even after the deployment phase, the change is still inevitable, of course, if you want your software to remain useful. That's why companies allocate most of the software budget to maintenance. In fact, statistics have shown that 40 to 90% of the total budget of software projects go to software maintenance. One of the ways to reduce the effort required for future change is refactoring. According to Martin Fowler, the father of refactoring, refactoring can be defined as a change made to the internal structure of a software to make it easier to understand and cheaper to modify without changing its observable behavior. To better understand this definition, I have here an example where we're trying to refactor a blob class. The blob is an anti-pattern found in designs where the majority of the responsibilities are allocated to one complex class, while the other classes are on simple data classes. This makes the code difficult to read and hard to maintain, and it can even affect the availability and functionality of the system. So to fix this problem, we try to identify or categorize related methods and fields, and we move them to new classes by using different refactoring operations, such as extract class, move method, and so on and so forth. This will make classes more cohesive, easy to read, and to understand. Now I would like to talk about the related work. Most of the existing work focused on improving code quality, such as removing code smells and improving internal and external quality metrics. Security-aware refactoring did not receive much attention. We have one study where the authors tried to implement a framework to detect potential vulnerabilities. However, they only used two types of refactorings, and they assessed the security by seeing the changes of accessibility of the method. In the second study, the authors tried to assess the impact of refactoring on the security of the system by computing the change in security metrics after refactoring. They validated their work using a case study, which means that the results cannot be generalized. In the third study, the authors used search-based techniques to find refactorings that optimize security metrics. However, they did not study the relationship between code quality and security, and they did not consider code quality as an objective when doing refactoring. Also, they validated their work on a case study, which means that their results cannot be generalized. Here we try to provide a concrete example that shows how people are more and more aware of the fact that improving code quality can actually decrease the security of the software. We mine the CVE security bug database, which is a repository where developers report the vulnerabilities they found when coding or using the system. We found a total of 269 security vulnerabilities that were introduced by code refactorings. This figure shows an example of a vulnerability from Apache Tomcat due to refactorings that improved the abstraction of the architecture. However, it caused information leakage, including session ID and the response body. This security bug impacted the confidentiality, integrity, and availability of Apache Tomcat in several releases between 7.0 and 9.0. This is another motivating example that shows how refactoring may improve code quality while making the design weaker from a security perspective. So this is a UML fragment of a banking system. A bank account can be either a debit or a credit account. And the interest rate constant in the bank account class stores the value of the interest rate of the credit account, which means that it's only used by the credit account class. The deposit and withdrawal operations have duplicate code that performs the transaction. So this code can be extracted to a new separate method that can be used by both operations. So both account number and credit card number are sensitive, and they are meant to be kept confidential. The developer applied the refactoring pushdown field by moving the interest rate constant from the bank account class to its subclass credit account. It also applied the refactoring extract method by moving the duplicate code to a separate new method called perform transaction, and replacing the old code with a call to this new method. So these refactorings improved quality attributes such as understandability, functionality, and reusability. However, they might have increased some security metrics, which reduces the security of the design. In this study, we have three main contributions. The first one consists of understanding the impact of source code refactoring on both quality and security metrics and the correlations between them. We also created a framework to recommend refactorings that find trade-offs between quality and security. And finally, we validated this framework on open source systems. For the metrics collection phase, we chose the QMOD metrics, which stands for Quality Model for Object-Oriented Design, to quantify the quality of the code. So they are one of the most popular quality standards for software systems, and we chose them because they are commonly used in industry and refactoring studies, and they were validated on hundreds of systems. Here we have the formulas for the different metrics, and they can be calculated using static analysis of the code. For the security part, we chose a set of 8 code-level security metrics that reflect the exposure of classes and methods that deal with sensitive information. These metrics can also be measured by static analysis. Now, to answer the first research question, which is related to the relationship between security metrics and refactoring types, we selected 30 open source systems. We picked them of different sizes and from different domains. We then ran a refactoring tool that improves only quality on these projects. We extracted data about the refactoring solutions. We then selected the solution with the highest impact on the different quality attributes and recorded its impact on the security metrics. Finally, we statistically analyzed the impact of the refactoring types on code security metrics. This table summarizes the correlation between the different types of refactorings and average security metrics. The results show either a positive or negative correlation based on the Pearson correlation coefficient in all refactoring types except for the move field refactoring. So the symbol ++ means that the Pearson correlation coefficient has a value higher than 0.5. Minus means lower than minus 0.5. Plus means that the coefficient is between 0.1 and 0.5, and so on and so forth. For each refactoring type, we filtered the solutions to keep only the ones containing that type and counted its occurrence within the solution. Then we checked the correlation between the appearance of the refactoring type and its impact on the security metric. So we have increased method security, increased field security refactorings. They both reduce the accessibility to the attributes, and therefore they reduce the attack surface. And that's why we have here a positive correlation with the security metrics. Then we have encapsulate field, push down field, and push down method refactorings. They reduce the abstraction of classes, and therefore they increase the protection of fields and methods. That's why we have a positive correlation with the security metrics. Finally, we have decreased field security, decreased method security, and extract class, superclass, I'm sorry. They either make the fields and methods overexposed, or they increase the abstraction of the code. So that's why we have a negative impact on security. The table shows the refactoring patterns that were found in solutions that improve the security the most. And the figure shows the frequency of the refactorings and the solution that significantly increase the security measure. We found that the most frequent refactoring types are increased field security, increased method security, and encapsulate field, which are the refactoring types that make the methods and fields less exposed and accessed, which confirms the correlation results. To answer the second research question, which is about the correlation between quality and security metrics, we ran a refactoring tool on the 30 projects. We recorded the impact of the refactorings on both the QMOD quality attributes and the 8 code security metrics. Finally, we ran statistical tests to understand the correlation between the different metrics. So this table right here shows the correlation results between security and quality attributes. For quality attributes which are understandability, reusability, functionality, and extendability are all negatively correlated with the security metrics. On the other hand, flexibility and effectiveness are positively correlated with the security metrics. This makes sense because, for example, when we want to improve the extendability and understandability of our software, we usually create more classes with child-parent hierarchy, and therefore we'll have more classes that have access to confidential information. This decreases the security of our system because when you have access to the parent class, you usually have access to the children classes. So to answer the third research question, which is about comparing our work with tools that improve only code quality, we implemented a tool that optimizes both quality and security. We run this tool 30 times on 5 projects to make sure that the results are statistically significant. Then we run the tool that considers only the Q mode attributes as objectives 30 times on the same 5 projects. And finally, we analyze and visualize the results. So our approach takes as input the source code or GitHub link of a project to be analyzed, and generates as output a list of refactoring recommendations that balance both quality and security of the software system. So the first component parses the code to calculate the security metrics and quality attributes. For the second component, we adapted a multi-objective search algorithm based on NSGA2 to integrate the security and quality objectives. And we selected this algorithm due to its ability to find trade-offs between independent or conflicting objectives. Finally, the user can interact with our tool to accept or reject the refactoring recommendations. So a brief overview about the multi-objective optimization algorithm. So NSGA2 stands for non-dominated sorting genetic algorithm. The objective of this algorithm is to improve an initial population of candidate solutions to a set of Pareto optimal solutions that are not dominated by any other feasible solution. Okay, so here, for example, if we take this solution right here and this solution right here, we can say that this solution is better than this solution because this one improves the first objective better than the second one, and the second one improves the second objective better than the first one. So it all depends on the needs and priorities of the users. Now we need to evaluate these refactoring solutions. And to do so, we considered 7 objectives. The first 6 are the relative change of the 6 Q-mode attributes after applying a refactoring solution. The 7th objective is a security objective. It corresponds to the relative change in the average of all 8 security metrics after applying a refactoring solution. And we combined the security metrics in one objective together because they are not conflicting, unlike quality objectives. So this figure summarizes the impact of refactoring solutions on the quality attributes using our security-aware refactoring tool, and another tool that only considers quality objectives. So the red box plot corresponds to the values obtained using our tool, and the blue box plot corresponds to the value obtained using quality metrics objectives without considering security. The tool that did not consider security improved the quality attributes slightly better than our tool. However, the difference is rather small. This figure shows the distribution of the security values in the refactoring solutions generated using our tool and an existing one that only considered quality. So the results show that the tool that has only quality metrics as objectives was not able to generate any refactoring solutions with security value lower than 0.18, while our approach was able to improve the security metrics to reach lower than 0.17. So here we need to keep in mind that our goal here is to minimize the security values. And the deviation may look small, but we should also keep in mind that the formulation of security metrics requires a lot of code change to slightly improve their values. So we evaluated our study using 5 systems that we see here in this table. So these systems have different sizes and domains, and 15 software practitioners participated in our survey. We performed a pre-study survey to collect background information about the participants. We also did an evaluation survey to evaluate the solution generated by our tool and its impact on both quality and security. And finally, in the post-study survey, we collected the opinions of developers about their user experience when they used our tool and the relevance of considering security when refactoring. We also asked them about their opinion in the possible correlation between security metrics and Q-mode metrics and refactoring and Q-mode metrics. So here we asked the developers about the importance of refactoring systems for security purposes, and the vast majority answered by either important or rather important. We asked them about the difficulty of using and interacting with our tool, and how difficult it is to understand the impact of refactoring on quality and security. And most of them answered easy and very easy. Here we ask the participants about the possible impact of each refactoring type on the security metrics. And according to them, encapsulate field can have the most positive impact on several security metrics. They also suggested that exact superclass will impact the security metrics in a negative way. So the participants also find that push-down method refactoring can improve several security metrics since it will reduce accessibility to the methods after refactoring. For our future work, we are planning to consider more security and quality metrics to extend our empirical validation. We are also planning to perform an empirical study to investigate the correlation between security metrics and the impact of improving one on the other. And finally, we are planning to validate our findings using more systems. Now let's see a demo of the tool we implemented for this contribution. First, we start by logging in. Here we have a dashboard that contains a summary of the quality and security computations for all the projects we have in our database. So this is a radar chart that compares the different quality and security metrics for the different categories of our projects. So here we have bar plots and visualizations of the quality and security metrics of the different categories of our projects. Now, to analyze one project, we first start by adding the GitHub link to its repository. We also write the name and the category of that project. Now, if we go to the projects list, we find the list of all projects we analyzed. And when we click on one project, you find the list of actions that you can perform, such as parsing, finding code smells, refactoring, and so on and so forth. And if we go to the project report, we find all the computations of the design metrics, Q-mode metrics, security metrics. So the red bar means that the project has a value less than the average value of that metric in its category. Green means that the value is better than the average. And the length of the bar indicates by how much it's better or worse. We also see the list of detected code smells. Then we have a radar chart that allows you to compare the quality and security metrics with the average value of the project's category. Then we have the dependency graph that shows the dependency between packages of the projects. Now we have the classes in that project and the quality and security metrics computations for each class. We can sort them by any metrics we have here. Then we have the graph of refactoring solutions and the different refactoring objectives. Then we have the solutions table where you can see the quality and security variations if you apply each solution. Of course, you can sort the solutions based on security metrics, understandability metric, or any other quality metric. If we click on one refactoring solution, we'll find the list of refactoring operations included in that solution. And we can view that refactoring or accept it or reject it. So if we click on one refactoring operation, we see the source class, the target class, and the change in the structure of the code if we apply that refactoring operation. And we can choose by either accepting or rejecting that refactoring, and we can add a description when we put why we accepted or rejected that refactoring. Okay, so this brings us to the end of my presentation. Thank you everybody for your attention. If anyone has any questions, please feel free to ask them. Thank you.